these were the operations we're looking at. Multiplication of two complex numbers. So if one complex number is written as Z1 equal to one complex number is written as Z1 equal to R1 times cos theta 1 plus J sin theta 1, or in shorthand notation like that. And the other one is written as Z2 equal to R2 cos theta 2 plus J sin theta 2, or shorthand like that. All you do is you multiply these two moduli and you add the two arguments. That's all. You multiply the moduli, and you, or if you if you're writing it out completely, this is how I write it. This is just the shorthand notation. With division of two complex numbers, you divide the two moduli, you get the quotient of the moduli, and you subtract the top argument, the bottom argument from the top argument, okay? Theta 1 minus theta 2. So that's important to bear in mind, okay, guys? Right, so just try and remember this part, or let me write it down again. And then it's fine, okay? So, yeah. Let me just say there that I'll just use the shorthand notation. So Z1, Z2, for the way Z1 and Z2 have been defined, it's R1, R2, theta 1 plus theta 2, and the division of Z1 by Z2 is R1 over R2, theta 1 minus theta 2. Right, that's it. So here you must understand that the nice part about this is that complex numbers written in exponential form, they obey the laws of exponents, okay? So the laws of exponents, just to refresh you quickly, laws of exponents. You guys know that exponential laws look something like this. If I say a to the m times a to the n, so just a recap on the laws of exponents, then you can just write this as when the bases are the same, you just add the exponents. When you divide a to the m by a to the n, you just subtract, right? And then if you say, what is the other one now? A to the n, all to the n, well, this is just an extension of the first law there on top. Extension of the first law on top. This is a to the m times n, okay? And then a, b, r, and s all to the m, a to the rm times b to the sm, okay? B to the sm. So so those are basically, in essence, three main laws. I was just adding, this is a sub, this one is just the sub law, okay? It comes from the others. Yeah, so basically that's it. So let's look at maybe some of these examples, guys, and there they've written it down. So I've just given some extra one there. They also have this one, yeah. Well, this one that I'm writing down is just a special case also. A b to the m. It's the same as this one, but this is just a special case. It's a to the m, b to the m. Okay, right. So so you can see with the complex numbers, they in exponential form they follow the same laws. Okay, right. And this is how they write it down. So if you have if Z1 is equal to R1e to the theta J1, theta 1j or j theta 1, right? And Z2 is equal to R2 e theta 2j or j theta 2, right? Then just reiterating this, guys. Z1, Z2 is equal to R1, R2, E, and then I take my J outside, and I have a θ1 plus θ2. Okay, and with division, it's basically what we have written down already. It's R1 over R2, and it's E to the J θ1 minus θ2. And then Z1, for example, to the N. Well, this is just R1 all to the N. R1 all to the N. And then it's E to the J N θ1. Okay, so those are your laws of exponents applied to exponential form. Okay, right. Let's look at example 2 then there, guys. Let's look at example 2. Let me just check if there are any questions at this point. Any questions in the chat? Okay, doesn't seem to be any question. There don't seem to be any questions, guys. Okay, so great. Let's just proceed then. Okay, right. So so what we consider is the following example. Example 2. Let's just do 2 problems from there, and then see. So we apply those rules now. Okay, all those laws. Right. So let's see. Let's see quickly. They say multiply. So the A part, let's do the A part and possibly the, let's do all 3. Let's do all 3 of them. A part says multiply. Multiply 7e to the 4,2j by 2e to the 2,5j. Right? And that's what we need to do there. And with the B part, divide 9e 3,2j by 2e to the 4,3j. And then the C part asks you to calculate, let me write it down here, calculate 4e to the j times 2,3 or 2,3j. And you must raise that, all of that you must raise to the exponent 5. Okay. And here are our laws for multiplication. Here are the rules for multiplication of exponential forms. Okay. Right. So you multiply the moduli and you add the arguments. With division of 2 complex numbers, you divide the moduli and you subtract the argument from the one from the other one, and you raise it to an exponent n. Well, you raise the modulus to the exponent n also, and then in the exponent you multiply by n, you multiply n θ1 in times the j. Okay, so that's all you need to remember there. So let's see the A part then. Let's look at the A part. So solution. Well, we can see there we must multiply 7. We must multiply 7 e to the 4,2j, and we must multiply that by 2e to the 2,5j. So what does it say? Well, 7 times 2 is 14, we know that, right? Those are the moduli, we multiply them, R1, R2, and then we must add the angles, okay? So we must add 4,2 to 2,5 and take out the j. And take out the j as the common factor there, okay? And then, so my new modulus is 14 for that product, and my combined angle is 6,7. combined argument is 6,7, okay? Right. And then with division, well, we'll just say again, we divide the two moduli 9 and 4. We divide 9 by 2, sorry, which will give us 4.5. So we'll have 9 e to the 3,2j, and we divide that by 2e to the 4,3j, right? So we'll have 4,5. It's 9 divided by 2. And then we just do a subtraction. We say 3,2 minus 4,3 and j. And then here 4,5. And then you subtract that, and you get minus 1,1 times j, minus 1,1j. And then for the last one, C, well, there you had to raise, for this one here, guys, you just have to raise 4 to the exponent 5, right? And then multiply in the exponent by 5, also there. So you just say j times 5 times 2.3. That's all you do there, okay? And then, well, that's 1024. And then that's E, and then that is 11.5j. 11.5j. Okay. So those are basically the straightforward, and the exponential form is very nice because you just use those laws of exponent easily. It's a very quick way of writing down a complex number. Okay, right. Then there's a set of activities on activity 1 at the bottom of, okay. Yeah.
Morning, sir.
Hi.
Can I please give you a question and just do it for me?
Okay, is it related to this work here?
Yes.
Is it related to this? Okay, let me just write it down for you then. Or is it something, is it a long question, or can I write it down? Can you give it to me and I write it on the line board?
Yeah, you can write it down.
Okay, so there's this question, let's say question. Okay, great. Okay.
If Z1 is equal to 5.
Okay, let me just see. If Z1, let me just do this nicer. Okay, just hang on for me. If Z1 is equal to 5, if Z1 is equal to 5,
E to the power 3 plus J pi over 2.
3 plus J pi over
2.
Okay, right.
And Z2
is
equal to 4 E to the power J pi.
E to the exponent J pi or pi J, okay? Right.
Find Z1 over Z2.
Find Z1 divided by Z2. Find Z1 divided by Z2. Okay, great. Okay, so we'll go about it in the same fashion. Okay, so we just adhere to this. Here. We will apply this directly. Okay, right. This one here, apply directly. So let's write it down now. So solution. Z1 over Z2. Sorry, I'll listen to solution. Right. so we need to get a quotient there, okay? Z1 divided by Z2. Well, we know that we must divide 5 by 4, R1 over R2, and inside there we must subtract those angles there, okay? Right, so if you gave me the correct question, so you'll just say 3 plus Then I will take out J, and I will say, because I am now dividing, right? I'm dividing, so I must then subtract those angles. Okay, I must subtract. So I will say pi over 2 minus 4 pi. Minus pi, sorry, minus pi. Minus pi. Remember, this is the one, this is the bottom angle. This is my theta 2, and this is my theta 1. Okay, it's my theta 1. Okay. So I've retained that. Let me just double check something before I. So because of the laws of exponents, yeah, I just have to subtract that, and that's fine because the exponent is there and the bases are the same. So it's the top one minus the bottom one. Okay, and then there I just deal with the components attached to the j to the square root of minus 1. So I would write this then as that. Is it 1,25, I think? And then I would say 3 plus, then this is minus a half. Okay, so it's minus a half. Oh, sorry guys. Minus j pi over 2. Yeah, that's how I would give it. Okay, I would write it like that. So it's just your laws of exponents that apply, and then you do that. Okay, so you just subtract. Remember, it says j theta 1 minus theta 2. Okay, right. But of course, we had a further. We didn't just have this only. We also had another real part there. Okay. For the top number, for the top complex number, for Z1 for the numerator, we had this 3 also, okay? But the fact is it's an exponent, so we subtract this exponent from this exponent. But of course, we just group together the imaginary parts, and we keep the real part separate, okay? And there's it. That's how I would do that problem. Does that answer your question?
Yes, sir, thank you. But then,
okay.
Could you please convert it back to polar form?
As it is, okay. Okay, I see what you say. You want it in this form. Is your hand up again? Okay. You would like it. Well, as it stands, then what you would do is this. Okay, this is what you would do then. Right. Great. You would do this then. You'd say, okay, 1,25, and then you'll split up. Because you see, if you write something like this to me, a squared times that, right? This is the same as a squared minus a2 minus 1, which is a, right? It's the same thing, because this is a squared over a, which is equal to a, right? So now what I will do is I will do this. Right? And then I will multiply e cubed by 1,25. I will multiply e cubed by 1,25. Also second function e, and then I raise it to the 3, and I roughly get 20 point, what is this, 20.086, something like that. 20,086. 20, so I've just split this up. I've just split it up because the base is the same. Bases are the same. So I just split it up. And then when I multiply 1,25 by e cubed on my calculator, I get roughly 20,086, roughly 3 decimals. And then there I keep my part. So there's my And thanks for reminding me about that. And there's my theta. It's minus pi over 2, okay? It's minus pi over 2. Okay, great. So, yeah. So you could have just written it inside there. Could have written it outside. You could also write it like this if you wanted to.
Sir?
Yes. Okay.
It's
can
going
also
to be
write
25,107.
Oh, okay. Oh, I didn't multiply by the 1.25 times 1.25. Yes. Thanks. I forgot to do that. 25,107. Thanks. I thought I missed something. Great. Thanks for that. But basically that's it. And then you can just write, you said 25,107, eh?
Yes.
25. Sorry guys, I forgot to multiply by the outside there. 25,107 roughly. And then you just say E, and you can just say J minus pi over 2. J times minus pi over 2, okay? That's it basically. But that angle minus pi over 2, if you add 2 pi to it, well, you get 3 pi over 2, which is exactly the same. Because you'll end up in the same thing. You can possibly write it like this also. In terms of positive angles, you can raise it as J, because now if you add 360 degrees, if you add 2 pi radians to this angle here, so basically you are currently here. So if you were to express it in terms of as a positive angle, you are currently here. Let's say you are here looking at the angle alone, where the angle is. The angle is here at minus pi over 2, sorry. The angle is here, minus pi over 2. But of course, if you go this way, it will be 3 pi over 2. 3 pi over 2. You now at minus pi over 2. But if you moved anti-clockwise, you get to 3 pi over 2. So as a positive angle, you write minus pi over 2 is 3 pi over 2. Okay. So you can write this, and there's nothing wrong with that. You can write it as the positive angle, 3 pi over 2. You want to, okay. But I mean, it's fine. You should keep minus pi over 2. It's not a problem. For the reasons I've explained now, with this negative, with the anti-clockwise and clockwise rotation, okay, you end up in the same position. Whether you move from here to here, you end up there. It's the same as you moving from that point to that point. You end up in the same position. Okay. Great. Okay, guys. Thanks for that question. Are there any other questions, guys, that you have? Then we can perhaps look at maybe. So that was a very nice question. So maybe let's look at activity 1, maybe 2 problems, and then we go on. Okay? So 2 more problems from activity 1, and then let's just see that. Okay. Let's select activity 1, page 119. Let's just select problem number D, number E. I think it's fine. Problem D and E. Yeah. So let's look at activity 1, guys. Problems D and E. And then, of course, you guys should feel free to ask a question. Activity 1, and we'll look at problems D and E before we go on. Okay. Let's see quickly. Let's look at D. They say perform the indicated operations. So it's 3E to the 2J, all to the 4, exponent 4. And then with E, they say 16E to the 6J to the 1 over 4, all to the 1 over 4, okay? Right. Let's see there quickly, guys. So let's look at this one. So there's a straightforward application of the law of exponents. So everything inside must be raised to the exponent 4. So 3 to the 4 is 81. And then we multiply that 2 in the exponent there, we multiply by 4, so we get AJ. And then for this one, well, 16 we know is 2 to the 4. And then we've got e to the 6j, and it's all raised to a quarter. And then we see that the 4 inside for the 2 cancels that 2 to the 4 to a quarter is 2. Because that 2 cancels that, and then the outside 4 is cancelled by that inside 4. But then we still keep it for when we deal with this part here. So it's e to the 3 over 2j. Okay. Right. So that's just your basic laws of exponents that you apply again. Okay. Right. Right, guys. So any further questions before I go on to multiplying and dividing in polar form? Maybe a question you want us to look at, like the previous student asked? Okay. Yeah. No one. Okay. So the next subsection is subsection 3. It's multiplying and dividing in polar form. So we just did the exponential form now. So this is multiplication and division in polar form. Okay. Right. So I'm going to write down, we've written down these results, but I'm just going to stress it again. Okay. I'm just going to write it down again. That's basically stuff that we've encountered, but it's okay. I'll just stress it again. So this is subsection 3, multiplying and dividing in polar form. So multiplication and division in polar form. Right, multiplication and division in polar form. So this is what we have. Let's see. So remember the relationship between polar and exponential forms. They just remind us that if you write something in exponential form, the complex number z is that, then in a polar form, you can write it as r cos theta plus j sine theta. Right? So that's the same thing. The first form is the exponential form, and this form is the polar form. So now, if we consider multiplication in polar form, so if you have complex numbers, say if z is equal, say z1 is equal to r1, oh, they're just stressing the point again, guys. Theta 1j, you know, in exponential form, we know how to write this product, okay? And z2 is, so they're just reiterating this. It's r2 e to the theta 2j. Then in exponential form, the product, so we're just reiterating this. It's just the product of the moduli. And then, of course, we add the arguments in the exponent. Okay, we add the arguments in the exponent. So for polar form, we have, so this is the exponential form. This is the exponential form. So for polar form, if you have two complex numbers, you've got z1. If z1 is equal to r1 cos theta 1 plus j sine theta 1, and z2 is equal to r2 cos theta 2, say, plus j sine theta 2, then the product z1, z2 is just r1, r2 cos theta 1 plus theta 2 plus j sine theta 1 plus theta 2. So that's just how you write it. Or you can just write this in shorthand notation as z1, z2 is R1, R2, and theta 1 plus theta 2. Okay, that's the shorthand notation. Where of course where Z1 is equal to R1 theta 1 and Z2 is equal to R2 theta 2. Okay, right. So it pretty much follows the same kind of reasoning as that of polar of exponential form. So the product of the complex numbers, well, we just multiply the moduli and you add the arguments. Okay, you add the arguments. So notice that in polar form they don't mind it actually, guys, if the angle is in degrees or radians in polar form. Okay, but in exponential form, they insist that these angles must be in radians. Okay, but for polar form they don't really mind. Radians or degrees is fine. Okay. So in polar, so the product of two complex numbers in polar form, for that you must multiply the moduli and add the arguments. Okay. So let's just do maybe 1-2 examples, and then we do an activity. In fact, let's just do one example and then go to an activity quickly. Okay. So let me just add another page. So this example that I'm going to do is example 3B on page 120. Okay, from your learning guide 1. So consider example 3B. Then we can look at an activity. Consider example 3B on page 120. Yeah, that's fine. So there they want you to evaluate 4 times. Consider example 3B. Right. So there they want you to multiply 4 times the cosine of 20 plus j sine of 20 degrees. And you multiply that by 3 times the cos of 70 plus j sine 70. So there we have the product of two complex numbers in polar form. Okay. So now what we need to do is just to multiply the moduli. R1, R2 is 12. And then all we have to do is then to add the angles. So we'll say cos 20 degrees plus 70 degrees plus j sine 70 degrees plus 20 degrees, so 20 degrees plus 70 degrees, doesn't matter. It's commutative. J sine 20 degrees plus 70 degrees. And then we find, so there's our 12. And the cos of 90 is 0. The cos of 90 is 0, and the sine of 90 is 1. Okay. Sine of 90 is equal to 1. And the cos of 90 is 0. Right? So that you'll have j, so the answer is 12j. Okay. So look at all that product of seemingly complicated, so perceivedly maybe complex number of complicated complex number looks like. It just reduces to rectangular form 12j, okay? With no real component, just an imaginary component of 12. Okay, guys, let me pause there, and before we proceed to activity 2, just check whether there are any questions from you guys in the chat box, or any questions maybe that you want us to look at. Okay. So yeah, so I think we'll just probably stop before the Morse formula. And when we meet again, we finish the Morse formula in some analytic geometry, which we will do very quickly, because I think the main points of the analytic geometry that you guys really should grapple with is the part relating to the ellipses, but not so much with the parabolas and the lines and the circle. I don't anticipate many problems there. Unless there's some specific problems that you want to ask me, we can also look at that. So perhaps my approach to that will be, what are your specific problems on lines, parabolas, circles, and ellipses. So I really want you guys to come with specific questions regarding those ones rather than me going through everything, okay? Because we need to also look at derivatives and limits and those things and integrals. Right. Okay, guys, so are there any questions then? Before I go on with activity 2, there are 2 problems there that we'll look at. And then I just want us to get to before subsection 4. I think that'll be okay. Okay, guys, no questions. Let's look at activity 2 then quickly. Let's look at both those problems and then see. So for activity 2, so let's just see activity 2. Activity 2. Right, let's see quickly. So here we say determine. And then there's A. Say determine A cos theta plus J sine theta. And that's multiplied by B cos psi. So B cos psi. Cos psi. Okay. Plus J sine psi. Right. Okay. So again, for the A part, well, you must multiply the moduli. A times B. And you just add the angles. Okay. And then you just say cos theta plus psi, right? Plus J sine theta. Because we're multiplying 2 complex numbers now, right? We're multiplying 2 complex numbers. So when we multiply, we just add the rule is add the arguments and multiply the moduli. That's all. So that's what we're doing exactly. Okay. So this is J. What is the sine theta plus psi? So I'm doing exactly as what we are required here. So we just multiply the moduli and we add the angles. That's all. Okay, that's what we do there. So we apply this in a straightforward manner. Okay, great. So let's see the B part. The B part asks you to determine. Okay, this is an interesting one. It says 3 times cosine of 30 plus J sine 30. And they want it all to be squared. Okay. So in this case, guys, you must just multiply that angle by 30, that angle 30 degrees by 2. So you can write it down the shorthand way, or you can just write out the whole thing. But what you'll do basically, you'll square the 3 there. That modulus, you'll square it. 3 squared. So it's 9. And for raising it to an exponent, all you do, you just say, okay, cos 2 times 30. 2 times 30 plus J sine 2 times 30. Right? And then you say 9, and this is the cosine of 60 plus J sine of 60. So we know from our special angles, that is 30 degrees and that is 60 degrees, you know, that's 1/2 and it's square root of 3. We know that the cosine of 60 is the sine of 30. The cosine of 60 is 1/2. So it's 9, it's 1/2 And then the sine of 60 is square root of 3 over 2. Right, so you can write it in that form. You can leave it in that form, or you can simplify further and multiply 9 outside by all those numbers. Okay, so you can say, okay, 9 times half is 4,5, and then you have j, and then you've got 4,5 times square root 3. Well, you can just say 4.5 times square root 3, and you get 7.79 roughly. 7.79 if I were correctly. J 7.79. Okay. So that's your result there, guys. Okay. All right. So the main point there was that this exponent here, the exponent here, you square the modulus 3 to get 9, and then inside those angles you multiply by 2. Multiply by 2. That's all. Okay. Let me just see the result for activity 2, guys. Activity 2. Where is activity 2 now? Activity 2. Oh, they didn't simplify it further. But they just stopped here, guys. What they did was they didn't go on and on. They stopped here with a problem. Okay, which is fine. We just went on and wrote it further in rectangular form, but I mean it was fine. They just stopped their way, right, with the tick. Okay. And then with the other one, yeah, the other one is fine. Okay, right. Okay, guys, before then I proceed again, let me just check whether there's any from your side, whether there are any questions. Why the one? And then we can probably stop maybe. So we just did example 3 now, and we did activity 2. Okay. So now let's get to division. Division in polar form. And let's see what that results is. And then we can maybe do activity 3, maybe one example, and then it's fine. Okay. So what I would propose is we do those and we stop. So let me just add another page and then see that. So this is the section 3.2. It's called division. And we're dealing with division of complex numbers in polar form. Okay. Division, polar form. So there we are. There we are. Okay. So let's see. So let's just write down the result. So if Z1 is equal to so we know the division for the exponential form. I'm not going to write it down again. I'm just going to write down the division for the we're just going to write down the division for, and I'm going to use the shorthand notation, the division for the polar form. Okay, so not the exponential form. So suppose Z is equal to that, R1, Z1 is R1, cos theta 1 plus J sine theta 1. And Z2 equates to R2 cos theta 2 plus J sine theta 2, right? Then Z1 divided by Z2, the quotient of those two numbers, can be written as R1 divided by R2, and it's cos theta 1 minus theta 2 plus J sine theta 1 minus theta 2. So there's subtraction occurring, not addition. So with division, we have the quotient of the two moduli, and we have subtraction of the angles. Okay. Unlike with addition, we had addition of the angles. Unlike multiplication, sorry, we had addition of the angles and multiplication of the moduli. Okay. So basically, you can also write this in shorthand form. So 1Z2 is R1, R2, and the angle is θ1 minus θ2. So this means the same. This means exactly the same thing, what I wrote down there, okay? Right. And again, guys, they are stressing that the angle for polar form, you may work in either degrees or radians. They are fine with that. But of course, with exponential form, you must work in radian measure, okay? So the main point to remember here is division of the moduli and subtraction of the arguments, okay? So let's look at example 4 on page 121, and then we do activity 3. Example 4. Okay, example 4, and this is on page 121, right, in the learning guide. So they want you to do this one. They say 6 cosine of 78, cosine of 78 degrees plus j sine 78. And that is divided by, and that you must divide by, let's see there, guys. And that you must divide by 3 cos 30, 3 cos 30 plus j sine 30. Right. So of course, the rule is get the quotient of the moduli and subtract the angles. So that's what we're going to do. So 6 divided by 3 is 2. When we subtract the bottom angle from the top angle, we get the cos of 48 degrees plus j sine 48 degrees. And then basically that's it, okay? Or in shorthand notation, you can just write it as 2. So it's R at 48 degrees, okay? Right. Then for activity 3 then, let's see if we can do those 2 problems then. And then we can stop there. I think it's a good place to stop before we start with the Morph's theorem. So, right. So this one, they say calculate A. They say 15 at 135 degrees. And we have to divide that by, so this is division of the polar form. We have to divide it by 3 at 75 degrees, right? And then the B part asks you to do 3 cos 20 degrees plus j sine 20 degrees, sine 20 degrees, and this is times 5 cos 10 degrees plus j sine 10 degrees. Okay, and then we have to divide that by, you guys please just double check whether I wrote things down correctly. And then we have to divide that by 2 cosine 30. So cosine 30 plus j sine 30. Right, so, and you guys will remember when we wrote these numbers in rectangular form, and when we had division in rectangular form, we always had to look at the conjugate of the complex number, where we had to multiply by the conjugate of the number in the denominator. But now things are relatively simple with the polar forms, though it looks a bit complicated, but things are relatively simple now, okay? So let's look at the top one. I hope I wrote things correctly, Seems fine. So let's look at this one here quickly, guys. Now, this is division of the moduli. So this is 5. And then we subtract the angles, okay, the bottom one from the top one. And that is 60 degrees. So 135 minus 75, 60 degrees, right? So that one was relatively straightforward. Let's look at this one. Here, I would first propose that you multiply the top part before dividing. You can do any one first, doesn't matter. It's up to you. You can first divide maybe the first factor on top with the bottom one by the bottom one and then multiply, or you can first multiply the top out. So I'm going to multiply out the top, the numerator. 3 times 5 is 15. And then I'm going to add those angles because I'm multiplying now. I'm going to add the top angles 10 and 20. So it's cos 30 degrees. It's cosine of 30 degrees. So I'm adding these angles, okay? Adding these angles. Plus j sine 30 degrees. And then I have to divide it by 2 cos 30. 2 cos 30 degrees plus j sine 30 degrees. And then 15 divided by 2 gives me 7.5, 7.5. And now I must subtract the bottom angle from the top angle, which is 0, right? So I've got cos of 0 degrees, which is 1, plus j sine 0, which is 0. Right? So this part gives me 0, and this part gives me 1. So my final answer is just 7.5, okay? Because the cosine of 0 is equal to 1. And look how simple that worked out, okay? So this was activity 3. Let me just verify my result here. Activity 3, yes, it seems fine, okay? Yeah, it seems fine. Okay, guys, so I just want to check before I close over the session. Let me allow maybe 5 minutes for questions, so forth. 5 to 10 minutes of questions. Anyone with any compelling questions? Thanks, student De Sousa. Anyone with compelling questions? Oh, there's a hand there. Okay, there's someone's hand. I'm not sure who it is. Okay, is it student Dana? Okay.
Yes, sir.
Okay, great. Thanks,
if we can go back to that other example the student gave where we
okay. Right. I'm trying to call it. Let me just check. I remember that. Okay. You wanted some clarification there.
Yes.
Let's see. I know I had it towards the end.
Yes,
this one. Yes. Okay.
So it will be the same. We'll end up with the same answer if we had converted that Z1. If we took 5 times e to the power 3 and made that our r, we would have gotten to the same answer, right?
If we had made so what I did, I multiplied e cubed with 5 over 4, and that's on UR 25.107 now.
Okay, then it would have made it a bit more. So then you just when we divide the 5e cubed by the 4, and that would be the r, the resultant of the r.
Okay, you just need to repeat it again for me.
So when we divided and we did that, we would have said 5e cubed is our new r for Z1, and we would have divided that by 4 at Z2.
Oh, okay. So of that product, for that we did, what did you do? We did a quotient, right? We did a quotient, okay? So then we had 5 over 4, right? And then, but of course she insisted I must write this back, and I like that reminder from her. She insisted I must write this back in exponential form. Yes. So as it were, I needed to have e to the theta j, but then I had some other things, and then I said, okay, let me split that E3, split it into 2 factors, okay? So, of course, keeping in mind the laws of exponents, I've done that. And there I've got theta j, see? And then, so therefore this part here now, I can shift this. This is a real number. I can multiply by that real number, which I got. And now I remain with my theta j. I remain with my theta e to the theta j. Okay.
Okay.
So this is my new r.
Yes.
This is my
So
new r for that quotient. Yeah. Yeah.
But we could have done that right from the start, no?
You could have done it right from the start.
Been the same.
It's just that I think she reminded me, but she wants it in exponential form. So I realized, okay. Theta j. Yes, I actually should have done it from the start. I should have done it from the start.
Okay.
It was a bit belated reaction from me, but fortunately she told me that she requires that in exponential form. So then, because it wasn't going to be okay the way I had left it, so I had to do that little trick, you know. And like I said, minus pi over 2, you can write it as 3 pi over 2 because you get to the same position in the complex plane.
Okay.
Great.
Thank you.
Thanks for that question. Okay, guys, any other questions? I think student choice. No, okay. There doesn't seem to be.